A guitar wants to kill my mama. So, this is my third take. There's a charm. Tertiary. Third time is charm. So, today I'm going to do the start of a thing, maybe. I don't know if I'm really going to do it. I always say I'm going to do stuff like this, but I haven't since the e to the pi thing. I don't care. Anyways, so, I'm going to do it eventually. Maybe not all of it, but yeah. Well, what am I talking about? Anyways, I'm talking about differential geometry. I want to do a differential geometry series, and go over it, talk about it. I originally just wanted to talk about differential forms and the change of variable theorem for like wedge products of differential forms and a change of chart when you want to change charts, right? And when you want to change charts of differential forms, right? But that I also believe that requires you to kind of talk about orientation and integration. So really, if you want to talk about it correctly, you have to use all of differential geometry. So that's my kind of thing. I mean, if you want to fully understand it, I feel like that. I mean, basically all of differential. You don't need like Lie derivatives or that crap. Lie algebras and Lie groups are for people in the LGBTQ community. All right, that's fine if you're in that community. But me personally, I like girls. All right. So first of all, to get an understanding of this, we have to talk about what a manifold is. I'm gonna call this a manifold. A manifold is a topological space, first and foremost. If you want to understand what a topological space is, should you look at my video? Do I even have a video about topological spaces? No. Just learn it. I don't know. Maybe look at my video. I don't know. I don't know how good it is. It's a topological space with three main properties. It's Hausdorff, so it satisfies the T something axiom. I don't know which one. It's second countable. Alright? And this is the unofficial, really. I don't even think this is really a good descriptor, but whatever. Locally Euclidean. I'm not going to write like the full. So I'm going to explain what each and every one of these are, right? So yeah, I'm going to explain this last, though. And ironically, I said this is like, has a lot. So what does Hausdorff mean? That's the easiest one. So really, what Hausdorff means is for two distinct points, right? We'll just call this a point of a manifold. It's in the manifold, yeah. Q, M. Q is not equal to M. They're completely different. We can build an open set, right, or neighborhood around each point, right? Such that both of those neighborhoods are disjoint, right? So their intersection is the empty set. So yeah, that's what a Hausdorff space is. So if there are two distinct points, P is not equal to Q, this implies that there exists these two neighborhoods such that they are disjoint. This is what a Hausdorff space is saying. Totally. So, hopefully you could understand what that is. Pretty simple definition. But if you do not, here's a quick answer. So, let's just say that this whiteboard is a topological space and a manifold, which it is. So we're gonna have a point right here. This is a point. This is technically a point on the space. Okay, just pretend this is infinite. This is just a little tiny point. Okay, and then this is another point, right? Then, obviously, they're different, and we can create two little pieces. We can cut out two pieces of the whiteboard, and this is a neighborhood, like a little section of the whiteboard, right? And look, they're disjoint, right? And that's what a Hausdorff space is. Most stuff that we work in is Hausdorff. You could actually have non-Hausdorff spaces, and it be not abstract, right? Where I found this out. I don't know, somebody told me that Hausdorff spaces are hard. Sorry, I just woke up, and also I have this little congestion thing. I just had the flu, and there's like I don't know. I went to the doctor and they said there's just residue. I'm not sick though. But okay, so for example, this could be a non-Hausdorff space. But most of them are Hausdorff spaces. But it is actually really hard to think about, because technically, what this makes how this is a Hausdorff space is that everything around it does not exist. Like the white space around it does not exist, and that's hard to visualize because it's hard to visualize what does not exist. Something existing in an empty vacuum it's hard to visualize, because even with space, I believe. Yeah, I don't know. It's just hard to kind of visualize stuff not existing. But I guess, yeah, you could say space and stuff. So I don't know why he said it was hard to think about. Anyways, but yeah, that's what a Hausdorff space is. Just don't overthink it. I don't know why I'm overthinking it. I'm sorry. Yeah. And then second one, which is probably the fundamental property of a manifold. So first of all, why are we even defining a manifold? I forgot to mention that. So the thing with manifolds is that it kind of helps us do calculus, like on geometric objects. Well, why do you need to define a manifold? Why can't we have a subspace of a metric space or a subspace of a vector space? First of all, subspaces of vector spaces, right? Most geometric objects are not vector spaces. Vector spaces are literally supposed to be linear. So when you have a curve, or literally just a curve. I mean, you could use an example of a circle. A circle is not a vector subspace. But you could extend this to a curve. A curve is not a vector space either. So you would need a metric space, right? But even at that, we want to kind of generalize it, because certain things are not as kind of easy, like a Mobius strip. So we want to kind of look at things locally. We want to generalize the concept of a geometric object, and at the same time do calculus on it, right? So here's the calculus part about it. So it's locally Euclidean. So what this says is that for every, this is the sign denoting for every, this is literally just translate to for every open set in the manifold. Right? We'll just say this is open in the manifold. There can be a function between the open set of the manifold and an open set of the Euclidean space, and this is Rn. R2 is a plane. The Cartesian plane. R is the real line, and R3. I'm sorry. And R3 is a space. This is R3. I'm in R3 right now. We are in R3. So it could be morphed into something like it is like Euclidean. It is locally Euclidean. Each patch of the manifold is locally Euclidean. Every little kind of thing, you could take a section out of it, and then, whoa boy, that thing is Euclidean. But, first of all, I forgot to mention what this type of mapping was. This mapping, the reason why it's like Euclidean, is because of these two properties. It is bicontinuous and bijective. I don't know why I blanked out on that one. If you don't know what bijective is, you're kind of gay. But I'll describe it anyways. I'll describe the short definition. Bijective function means that it's one-to-one and onto. It is injective and it is surjective. Right? If you don't know what that means, then you probably shouldn't be here and just learn it up. Just use Wikipedia. Wikipedia is the best resource for math. I mean, even though, it doesn't have a reputation, yeah, I don't know why I'm explaining this. Everybody knows that Wikipedia is a good resource for math. Every person who's competent in math knows that. And it's bicontinuous, which means that the function is continuous and the inverse function is continuous. I'm going to just say C for short. Yeah, so the function is continuous and the inverse function is continuous. C for short. So you might be asking also, well, how do we even know what continuity is? You could look at the topological definition of continuity. And the topological definition of continuity is that a mapping is continuous if for every, from two topological spaces, for every open set of Y, the inverse function of every open set of Y is a subset of X, right? Which is basically the same thing as epsilon delta, which is a generalization of the left and right thing for continuity, right? Just think about it. Think about it. Think about it. So what this is a homeomorphism, and that's the whole topology thing. And oh my god, that's what topology is about, a homeomorphism. Even though it's not really, and they know what they're saying, they should be more specific because it's actually algebraic topology, not topology because you're confusing people, and when they get into point set topology, they're like, where's the homeomorphisms? I don't see any homeomorphisms. This is just set theory, but advanced. Because you are confusing people and you need to shut your trap. Fucking say it right. Homeomorphism. That is the little gluing and cutting thing. That's why we say a donut is the same thing as a coffee mug. Because we can build a function between a donut and a coffee mug such that it's bicontinuous and bijective. We can build a homeomorphism between the two sets, right? So it's really deforming it. So I will use the intuition here. It's deforming it without squishing, without cutting or gluing it. Yeah. And more on that is with the quotient topology. If you want to know why that is so, you could look at the quotient topology, which and the quotient map and its properties. Oh my goodness. Okay. So that's what we mean by locally Euclidean. So the final thing that kind of brings this around is that with every topological space, there is a basis. Just like a vector space has a basis, I hat and J hat, right? Those generate R2. Or, generally we can just go to E1, E2, all the way to En, and that also generates Rn. It spans Rn, and they are linearly independent. A topological space has a basis akin to that, right? Which also works as a vector space basis. So So we're gonna say that this is the basis for, my goodness, I don't know if I did the calligraphic B right. So we're gonna say this is the basis for n, right? And this really says that all this is saying is that the basis is countable. It's a countable set. The basis is a countable set of stuff, which is saying that this is bijective to the set of positive, of positive integers. This has the same amount, cardinality, amount of items as a set of integers. If you want to know more of what bijective is, go see Vsauce's video on, this is the thumbnail I think, on how to count past infinity. I really like that video, and I think I like his bald head, because he makes a lot of good topology videos, and I had no idea until now, because when I watched his videos I was a mathlet. So yeah, that's what it is. So a topological space, intuitionally, bring this all together now. I believe somebody told me this. It's like a quilt. I don't know if it was the same person. And it's a topological space is like a quilt. You bring a bunch of patches of Euclidean space, deform it, and then glue them together. Glue them together. Like if you look at Jean's, Billie Jean has got my love, and she says, I am the one. If you look at Jean and those little patches, it's a lot like that. You're patching a bunch of pieces of Euclidean space together to make a topological space. Like it could be, it could be 2D patches, it could be 3D patches, it could be like this thing. I want to make this whole bundle here, and then patch them together, glue them together, wrap it around, I don't know. Boom, we got a manifold. You just bring a bunch of pieces together and glue them together from Euclidean space, and then you got a little piece of a geometric object. And it is locally Euclidean, right? Which allows us to look at calculus. Why does this allow us to look at calculus? Why can't we say it's globally Euclidean? Well, because of this. Locally Euclidean, notice how calculus only works at local things. By definition, where it looks at infinitesimals. It looks very locally. You only need a patch of something to look at the calculus of it. Hence, differentiable at a point. Not differentiable, differentiable at a point. And then we could also, we could look at the whole function as differentiable. But we usually look at differentiable at a point, right? So, this allows us to do calculus on it, because how else do you do calculus? Do you want to do calculus on a set of GBA? How do you even take the derivative of GBA? How do you take the derivative of your mom? What the fuck does that even mean? So, if you want to do calculus, we gotta have locally Euclidean, and this also works because the set of complex numbers because they are also locally Euclidean. They are also Euclidean-like. But yeah. So, yeah. That helps us do calculus. And maybe asking, well, how do we even do calculus? How do we even, how do we even see if a manifold is differentiable then? Well, good thing you ask. If you did ask, didn't care, didn't ask, plus, you were cracking. Okay, so, the way we do this is that, you notice how I said each thing is locally Euclidean, right, from a manifold? Well, if it's locally Euclidean, and you know that little function we were talking about, which we call the homeomorphism, right? Why can't we just say the basis is made of stuff, of open sets, right? And we can pair it together with the homeomorphism, which associates with Rn, a piece of Rn. So, boom, we did it. And we're going to say alpha for each and every one, right? We're going to index this set. Alpha is just the identifier, because what if we want to say 1, and we want 2 different neighborhoods, or 2 different open sets, right? So we're just going to say alpha as an identifier, because there's going to be multiple open sets which generate the manifold, right? So now how do we say a manifold, a whole manifold is smooth, right? So to do this, we would obviously have to, smooth. Oh, fuck. Oh my god. I did this so better. I did this way better for the second one. Smooth. So what is smooth? Or it's basically differentiable but generalized. So this is how we denote a smooth. We say this is the same thing as saying smooth. This is literally the same thing as saying smooth. This is just a shorter way of saying it. Which means infinitely differentiable, right? We can take the derivative, second derivative, third derivative, fifth derivative, etc. Right? F of x equals x is smooth. And f of xy equals xy is smooth, right? We could take the partial derivative of x, which is going to be equal to y, and then we could take the partial derivative of x of y, which is going to equal to 1, and then we could take the partial derivative of x again, and that's going to be equal to 0, take the partial, etc. All it just goes infinitely, right? So that's what we mean by infinitely smooth. I mean, infinitely differentiable, my god. Don't overthink it with that, just say infinitely differentiable, and we'll be fine, right? Pretty straightforward definition off the bat, right? The other thing is just a precise and rigorous definition. I just kind of, not really, but it's closer to that. But yeah, so how do we check for that? Well, how do we even take the derivative of an open set we don't even know is Euclidean, right? We said we could look at Euclidean, so we're going to have to kind of manipulate each part of this to make it Euclidean. Also, for shorthand, I'm going to call this a chart or a coordinate system. And I'm going to call this entire set of ordered pairs in the atlas. Right? Coordinate systems, self-explanatory, because it kind of maps it to another piece of Euclidean spaces. It charts it, really, like a map. It maps it. I mean, it's really hard not to, I don't know why I'm trying to explain it. It's fucking straightforward. So yeah. So we know that each alpha maps u of alpha to this alpha, which is an open subset of Rm, right? So we want to get the domain to be an open subset of Rm, right? So we could take 2 charts, right? Which maps U1 to U2. Oh, wait, I'm retarded. U1, which is Rn, and then U2, I'm not going to write that out. So, to do this, right, we want to kind of compose the 2 functions, right? And we're going to say, and we're going to use the inverse of this function, which maps, etc. So, we say that, now we're going to define something called smooth related. These charts are smooth related, right? If we take the composite of the first chart and the inverse of the second chart, which will map us, U2 intersection Jesus fucking Christ. 2 U1. We denote the intersection because of the limiting factor that each of them are dependent. Right? Jesus Christ, I'm retarded. The fact that these two open sets are disjoint means that... Okay, so, Jesus Christ. Oh my god. So... Fuck, I'm so retarded. Yeah, it's self-explanatory. Fuck, I don't know why I'm so retarded. So, oh my god. So we take the intersection because those two, we're trying to get them to map to each other. So this one maps from U2 to another piece of the Euclidean space, right? This one maps from U1 to another piece of the Euclidean space. Anything outside of U1 would not make sense at all. So, and would not be a homeomorphism at all. We don't know if it would be a homeomorphism. So to maintain this, we take the intersection of both so that they comply together and they're all a happy little family, right? And we say they're smooth related if this function is smooth. Boom. Oh my goodness. I don't know why I'm fucking... Oh, I'm spazzing. I'm spazzing out. I'm acting like an autist. So we say these two are smooth related to... Oh, and, of course, we want to change the domains and look at the other piece of them, right? Because who knows? You know, the inverse mapping is not always going to be differentiable, right? The mapping could be differentiable, but the inverse matching might not always be differentiable or even a function at all, right? And keep in mind, we are looking at, we're trying to look at the entire manifold. So two charts are smooth related if these two functions are smooth. These two specific mappings are smooth, right? And we can test that easily since they are both a mapping from a piece to a Euclidean space, and the image is a piece of a Euclidean space, which is like a standard function f of R2 to R, right? And which we can easily differentiate and easily check, right? So that allows us to check it with that. And that's how we define smooth related, right? Jeez. Okay. So, next, right? Oh, jeez. We say that a manifold, then, is smooth if it's paired with a maximum atlas, right? What a maximum atlas is, it's the largest atlas that can be made on the manifold, right? Of smooth related charts, right? It's the largest amount of stuff, the largest amount of ordered pairs, which can be made imposed on the manifold, which maintains that each chart is smooth related, right? So this atlas, we'll denote an atlas by this, and this means that every single possible atlas will be a subset of that atlas. This atlas is not a subset of any other atlas, right? And of course, again, it contains smooth related charts, right? So, obviously, this helps identify what is smooth because this kind of helps us create a basis and look at each little piece of the manifold and each variation of the manifold, right? Yeah. Yeah. But actually, you do not need to kind of build a... Let me look at that. I remember this. I totally forgot it though, because it was just not really important. But you actually do not need a maximal atlas all the time for a smooth related manifold. Yes. I don't see it. God damn it. But yeah, obviously we wouldn't need a maximal atlas all the time, but this helps us kind of get the base case, because we later find out that I'm not gonna say later find. Right now, there's actually a theorem that says that every smooth atlas with smooth related charts is contained in the maximal atlas, which is, I mean, pretty easy to kind of see. I don't know why the fuck it's theorem. Hold on. Yeah, it's contained in a unique maximal atlas, which is different. So we don't need to say that we don't need M to be paired with a maximal atlas for it to be smooth, but that helps us with the base case. So we define a smooth manifold with a maximal atlas, right? First of all, right? To kind of say, okay, every little piece of the manifold, right, must be smooth, right? Then we realize that, well, we could have smooth related charts and smooth related smooth, which is a smooth atlas, which is an atlas with smooth related charts, Jesus Christ, which is contained in the maximal atlas, right? So with this, we can just kind of build a basis for the manifold, right, of smooth related charts, which generate the manifold on its own, right? We don't really need a maximal atlas, as we kind of just come to find out, right? But this is the base definition. I don't know actually where I got that though, because it doesn't even say it here. I don't know, maybe I'm autistic. Yeah, it's pretty odd. But yeah, so really though, we'll find out, yeah, really though, what it says is, what I'm trying to say is that the existence of any atlas, right, with smooth related charts imposed on a manifold, right, will do, right? And this also brings us to coordinate systems. I forgot to mention that there could be different atlases, obviously. So with different atlases, we can build different types of charts, right? So an example would be R, right? R, M, theta. Or the standard Cartesian coordinates, X and Y, right? You can have those two different charts, which kind of build Rn, but they kind of look different. So we can kind of rotate the manifold differently, or have a chart where the manifolds kind of differently, it's just different, it's blah, 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 blah. It's just different in a way. It's just a different coordinate system. My bad. Jesus Christ. I don't know what, I look like an idiot right now. Okay, so, yeah. Okay. So, the final thing I want to say is a function between two manifolds. A function between two manifolds is differentiable if, right, we take a piece of the chart, we'll say this is an atlas for n, right, x of I, and we'll say this is the atlas for m, which is y of I, or just say y and x, right? So, we then say that they are differentiable if we take the, I believe, yeah, composition of this. Composition of y. If this is differentiable at that point, then I think that works. It makes sense. Yeah. Hold up. That's actually perfect. Yes, win. Epic. Dude, it makes sense. Alright. So if this is differentiable, right? What this does is it works on, so for every atlas in the manifold, right? Or we could just say this is, for every chart in the manifold. My bad, not every atlas. That's retarded, because that would just make, we already said. So every chart, so the manifold has now, again, we said a chart imposed on it, right? So, I mean, an atlas, Jesus Christ, an atlas imposed on it. So, for an atlas opposed on it, for every chart, right, we look at every chart, and if this is differentiable, then the whole function is differentiable. Alright? Alright? Good. So, what I was coming to, right, obviously, was that X maps to a piece of the Euclidean space. X is a homeomorphism to a Euclidean space, which will make it easier to differentiate the image. Boom, we have the image, right? F and the image. But now we want the domain to be occupying the Euclidean space. So what we do is we take a piece of M, but F can only work in M, right? We don't know about any piece of the Euclidean space. So we're gonna have to reverse Y, or the chart of Y, so that it maps from a piece of the Euclidean space to M, right? So this goes to the piece, now this goes to the piece of Euclidean space, to M, to a piece of M, which F turns into a piece of N, which then X turns into a piece of a Euclidean space. We can kind of cut out the middle with the composition, and then that just becomes a piece of the Euclidean space to the piece of the Euclidean space. And then that defines a differentiable function between two manifolds. And I think that's it for manifolds. Yes. Well, smooth maps. I see. Okay, so yeah. But that's the time we have. Alright, thank you for watching.